Hello, my name is Wyatt Carbonell, and I've just finished a summer research project at the Cornell Laboratory for Accelerator-based Sciences and Education. In this video, I'd like to tell you a little bit about the work that I did. Many people have heard about particle accelerators, devices that, well, accelerate particles. They range from massive, like the Large Hadron Collider at CERN, to relatively small, like the cathode ray tubes in old televisions. There's a very similar thing called a storage ring, which, as the name implies, tries to store these very fast particles for as long as possible. The Cornell Electron Storage Ring, also called CSER, is one such device, which confusingly doesn't store electrons at all. It stores positrons. Inside the storage ring, a large number of positrons travel at very nearly the speed of light, in what's called the positron beam. A large number of magnets bend, stretch, and squeeze the beam to keep it moving around the ring. In CSER, we store the positron beam for as long as 6 days, and in that time, each particle travels around the ring around 200 billion times. This means we need to understand what's happening to the beam very well. Even small inaccuracies will cause problems after that many turns around the ring. One of the most important things we need to know in some form or another is how big the beam is. If it gets too big, particles at the edges of the beam will hit a wall and be lost, and for some things like generating high energy X-rays, we want the beam to get as small as possible. More specifically, the beam tends to be very flat, so we usually only care about how wide it is. Luckily, we can use computers to simulate how wide it should be, but how would you go about measuring it to make sure? Well, only one reliable method is currently available, and it amounts to taking a picture of the beam. As light particles like positrons travel in a circle, they emit light, called synchrotron radiation. We can set up a specialized camera to take a picture of this light, and use what we see to determine the width of the beam. This has a few notable downsides. If the beam were made of heavy particles, like protons, then there wouldn't be enough synchrotron radiation to take a picture of. Also, to even make this work, you have to install this specialized camera, which only works in one spot and may or may not be used for anything else. I worked this summer on developing a new method to measure the width of the beam, which we hope will address some of these problems. Our method isn't quite finished yet, but here's the idea of it. Instead of using any new equipment, we're using sextupole magnets. There are already 76 of them in CSER to help keep the beam stable. If we change the strength of the sextupole magnet, we'll also kick the beam to a new orbit, differing from the original by only a few millionths of a degree. It turns out that this kick is related to the beam size, as well as the position of the beam. By measuring the position and trajectory of the beam, we should be able to calculate a beam size. This avoids the limitations of synchrotron radiation and works at all 76 sextupoles. I'd like to thank the National Science Foundation for providing funding for this research, and the Cornell Laboratory for Accelerator-based Sciences and Education for their amazing research opportunities. Thank you.